Welcome everyone to the AI for Trees challenge. We are here today to show you guys the final presentations of our 10-week journey. Before we start, I would like to thank our partners for this challenge. We have Sander here from Just Dig It, who spend their efforts in regreening parts of Africa with their rehydration goals. We also have people from the Vrije University of Amsterdam. I believe Tom is here, and otherwise he was traveling today, so he will try to be here. And at last but not least, Seafruit, who has helped us with labeling a lot of the images. So big thank you for their efforts, and I would like to start the presentation. So today you will hear from me. I will introduce the challenge. Then we'll go into the data enrichment team by Melanie. As a second presentation, we have from Michele the drone model improvements. And finally from Lewis, the presentation from the satellite team. And in the end, I think Sander will have some nice closing words for us. If you have any questions throughout the presentation, please raise your hand and we will come back at you as soon as we can. So I see a lot of unfamiliar faces as well. So for everyone who doesn't know us yet, we are Fruit Punch AI. We are the global AI for Good community. And we are building the AI for Good community because we believe that to solve humanity's greatest challenges, we need to educate AI engineers at scale with an ethical and sustainable mindset. The way that we do this is by organizing AI for Good challenges, of which the AI for Trees is one. We aim all our AI for Good challenge towards the Sustainable Development Goals. And as you can see, we have challenges, for example, in the wildlife, coral reefs, and AI for Earth domain. We are building a lot more challenges, so if you're interested in maybe joining one in the future, then make sure to keep track of the progress that we're making with Fruit Punch. The partners I went over already. So we're working for 10 weeks very hard with 3 teams, and in total 12 AI engineers reached the finish line. And together we've spent more than 1,000 hours of engineering work in this challenge. And the goal of this challenge was to create a machine learning model for automated tree detection and segmentation on drone and satellite imagery. So we started this challenge on the 13th of July, and we are finalizing it today with the final presentations. The teams will still have 2 weeks left for all the reports and finalizing all their models. Just to get to the ultimate result for the challenge. But what was this challenge about? Well, 10 weeks ago, we started off with Just Dig It with an effort to improve their already existing drone model. So Just Dig It aims to regreen a lot of Africa, where they, by using local efforts, they try to create more green in now deserted areas. In order to effectively do this, they need to count the individual trees in an area so that they know how well their efforts are actually increasing the biomass. So as they do it now, they train a lot of locals to do surveys around farms and in areas where they have been trying to put a lot of regreening. But this costs a lot of man hours, can be inaccurate at times. So they are aiming to improve upon this with drones, or eventually even with satellite imagery. So you can imagine that if you fly with a drone over a large area with trees, it's going to take a lot of time to individually count all the trees. And therefore, we started the challenge to improve the counting of trees with AI, and eventually even to be able to translate a model that we've trained on drone imagery to also start looking at satellite imagery, and from there be able to count the individual trees, and from there calculate the biomass that we're actually improving. So now that you know what the challenge is about, I would like to give you the floor to the first team, which is the data enrichment team. And I believe that Melanie is here today for us to present.
Yes, I'm ready to present. Okay, well, I'm Melanie. I'm presenting today on behalf of my team, the Data Enrichment team, to tell you a little bit what we've been doing the last 10 weeks. And let's see, here is the team, just for you to see. We have been working together, collaborating, and having good sessions to talk about the next steps in the past few weeks. And we've all done different tasks in this towards data enrichment. Let's see. So where we started off, when we had our first meeting, it was we had guest Tom Eames from the University of Amsterdam, and he told us he had this big data set of 40 drone images from different sites in Africa, and they were partially labeled by himself because it's a pretty big job. So you can see here one of the examples where he labeled maybe around 30 trees, but yeah, wasn't able to finish the annotations. So a lot of trees are unlabeled here. At the same time, he also collected height data on these trees, and so far nothing has been done with this height data yet in terms of the models that have already been created. And that was part of this challenge to maybe work with that. So we kept that in mind at the start of our task. And then, well, for us as a data enrichment team, the goal is pretty simple. We want more labeled trees because we saw that, yeah, this partial labeled data is a start, but it would be very beneficial if we could have the whole image completely labeled. So the simple goal that we started with, how can we get more annotated trees? And we came up in the beginning, we started with four options. One of them being manual labeling, and we considered this especially because we also had we knew that we had some labeling partners available who could possibly do this. So that was one of the big options that we were considering. We wanted to look at existing data sets, so other data from the data that Tom presented to us, to see if they had trees labeled in the same way as Tom had. We had a thought about self-supervised labeling. This, I believe, Lynx has also performed this on some other data by Just Dig It, but it hasn't been performed yet on Tom's data set. So that was an option. And the last option was to perform data augmentation to increase, because we have 40 images, we were thinking we should maybe use this option to increase even more the available data. And right now I can present you two options that we really worked out and have been working on these past few weeks, because we had a look into existing data sets, but we found that we really wanted to have these trees that are segmentable. So you have the tree shape instead of just a bounding box around the tree. And we found some public open source data, but mainly bounding box data, or the trees are the ecosystems were so different that you wouldn't they weren't comparable to the trees we're seeing in the images Tom provided us and Just Dig It provided us. So we lost existing data sets, and then with the self-supervised labeling, we didn't have enough expertise in the team, so we also dropped that and decided to focus on manual labeling because we had a partner available, and also data augmentation, something that we were eager to work on and had the skills to do. So the first one, manual labeling, we have to give a big thank you to our partner, CFRU.IT. They have spent a lot of hours transforming, as you can see, the partially labeled data to a completely annotated data set with, as best as they could, capture all the trees in an image. And one of the things that maybe you can see some very easily identifiable trees, but also some very small dots. and this was important. We wanted to also have as small as possible trees available. So we one of the directions we gave, or instructions we gave, is to really focus on these smaller trees, and just let's say we are okay with if some shrubs are maybe labeled as trees, because it would be better to have all small trees labeled. So that's why you see a lot of small dots here as well. And then for us, the task was to do quality insurance on this data. So we would have a look at the labels that CFRU provided, and we had a check just a randomly sampled check of a couple of trees in each image, and we used the digital service model there. So this is the height data of the tree. So each image has a height image complementing it. And we did ask CFRU to also look a bit at the digital surface map, but they had a lot of work already with the tree. So I think for us, we really used this digital surface map to do the quality insurance, to have an extra check. And then maybe, just to have a bit more idea of what it entailed. What we found, for instance, is that some trees were missed, which makes sense because there were hundreds of trees. So it's very likely that there were some trees going to be missed in the images. So I and we and the team ended up adding these to the labels ourselves. And we found also some trees that maybe were grouped together. You can see here, I'm not sure if you can see my pointer, but on the right side of the image, there's a tree with two quite different colors, the smaller one. So we also separated those kind of cases. And with the small trees that I focused on a little bit earlier, it was quite difficult at times, I can imagine, because the bright colors might indicate tree. But for instance, here in the middle, you can see an annotated tree that we ended up removing because it doesn't have any shadow. And you can see also in the height map that it is black, which means the height is about 0. So we ended up checking for mainly these things, the small trees and the trees that were maybe grouped together, and trees that were missing. Those were the three things we checked, and in the quality assurance, you can see that it's quite a task to get these trees properly annotated. And then just want to have a quick word about augmentation, which is a task that one of my team members mainly performed, and she focused on setting up the scripts to transform the images that we have, to do position augmentation and color augmentation. This is something because the labeling has taken so much time. It has not been, these augmented images not been used in the models that the other teams are going to present yet, or that someone will continue with it because it will give a lot of extra high quality data. And then I come to, I guess, our proud result with, of course, the biggest contribution here from CFRU. They counted 16,102 trees. So I think this is going to be a really nice data set for people. And I believe we're going to, it's going to be open source. So hopefully we can present it somewhere and other people can make use of it as well. But that's the biggest, I guess, achievement here for us for this challenge. And then to conclude, we found out labeling trees is resource intensive. So our partners had to invest a bit more time than they thought they would, because 16,000 trees manually labeled is quite a big job. But it's quite high quality, of course. For us during the quality assurance, we found that using both the RGB and the digital height map, the surface model, was most useful, because you can if you're unsure about a small tree actually being high enough to be a possible tree, you check the DSM. But if the height map doesn't give enough, you can see the colors, and the colors can be very good clue on how to separate overlapping trees. So really using both visual cues and height cues is key, and maybe is also a lesson for the model, that we need to combine maybe those two features. And then lastly, we want to hope in the next step that we can use the augmented data to improve the models even further. And that would be it for the data enrichment team.
All right. Thank you, Melanie. I didn't see the number yet of the trees labeled, but that's very impressive. And I'm sure indeed that it's going to be of much value for everyone who's going to train any models on it afterwards. I see Sander has a question.
Yeah, I'm not sure if this is the right time for questions or that's going to be later on.
No, sure, go ahead.
Oh, great. Thanks for the whole team. Amazing effort to label so many trees. Definitely useful for our purpose, but I like the fact that you're going to make it open source so others can use it as well. So awesome. I had a question about checking the quality of the labeling. Did you do that fully manually, or did you have an automated way of checking or verifying the quality of the labeling?
Yeah, we did that manually. So CFRU did the labeling, and our team here for the challenge, we set up a quality protocol to randomly sample a number of trees in each image, and look for these three main things, which are the small trees and the overlapping trees. But we had a little protocol to all be on the same page within our team. Yeah.
Yeah. Oh, awesome. Thanks.
All right. Any other questions for the data enrichment team? Otherwise, you can put them also in the. Oh, yeah. I see one more question.
Yeah, hello, hi, I'm Swarnlata, and I actually have a question that if I want to use this data set for, creating a model just for small trees, let's say. So as I could understand from the presentation, that whatever labeling was done manually, from those you are using like height 0 to consider that those are small trees. So is it possible that there are some false negatives, that some labeling are just no trees, but we just, if we are filtering just for small trees, so we come up with those kind of labeling which are not really small trees? Or how accurate could it be for using this?
Okay, yeah. So I think there's definitely some mistakes made, because sometimes the height map is not 100% accurate. It's created by photogrammetry. So and Tom has explained to us. So he used photogrammetry, but if trees move in the wind, then you could possibly miss them completely because you only use a couple of photos from different sites, and if it moves, then you get a very distorted height picture. The height map is not I'd say the holy grail. Tom said so. So that's why we really combined that with the visual and the height together. But sometimes it's still tricky. So I think it'd be very difficult to make a perfectly labeled set, because also we had within our team sometimes some different opinions, maybe. I think because the small trees were such a priority, it would be better to catch them all and have a few false positives. That was the idea that we had behind labeling it like this. So I hope that answered your question.
Yeah, sure. Thank you so much.
Yeah, and maybe to add on Melanie, indeed, that's what we discussed, and that is the preference for just DigIt. So we'd rather have a little less accuracy on the smaller trees, but are able to detect them. And then we have to accept that smaller accuracy. But at least we can say something about that then with some more uncertainty. And about the discussion, definitely there are going to be false positives and false negatives. Even being on the ground, sometimes it is hard to distinguish, well, is this thing which is growing there, is that a bush or a tree? It's hard to see. And sometimes you can't tell if you, then you really need to be an ecologist or a forester to determine the species and see what it will grow into. So it is a tricky thing that we are working on, but I'm well, based on the results that I've seen so far, I'm really impressed by it. So well done.
Great. I see another question from Michiel.
Yeah, hi. Just one little question. Thank you for your presentation, and so sorry if you already mentioned it. So are you just trying to detect any tree, or are you trying to detect the trees by species?
We are detecting any tree, yeah. So I also had posed a question to Sander before, because there's a lot of dry trees, as in trees without leaves in the images as well. But that's just, depending on the season, the trees have different times of having leaves. So we included all the trees, not separating on species, because the number is more important, I believe, than having an idea of which species there are. Yep.
Yeah. All right. Thank you.
All right. Then I would like to continue with the second group. So for the second group, we have Michele, and he is going to present how our team improved the drone models.
Yeah. So hi, I'm Michele from the data team. We are few, but we are really good, actually. It was very nice to work with Sai and Natalia and John in the last weeks, especially because we really worked hard. So I want to thank them in front of you all. And then let's move on to what is our task. Our goal was to create to improve the performances of the tree detection model that was currently used by Just Dig It, and to create in general a model able to detect trees based on drone data, which can be RGB data or height data, so digital surface model data. I think that's how they are called, the height data. Why does this matter? Because a good model can detect trees in a faster fashion than a human-based approach. This can enable to identify trees, but also to see how big they are, how healthy they are, and how many they are. This can help Just Dig It to track how well they're working on, like how well their efforts are going, and it increases their accountability. In exchange of more accountability and optimized efforts, Just Dig It is able to grow both more trees and grow the donors' trust in Just Dig It. Finally, all these should eventually lead to more trees getting planted and the Earth becoming a more sustainable planet. More in practice, what did we do about modeling? So we had different ideas. The first idea was to transfer learning a model that's called DeepForest that is based only on RGB data. Then second idea was to use to create a new model based on UNet architecture. And we created 3 models with the UNet architecture, one with RGB data, one with height data, and the last one with FOFI data combined together as an input. And finally, we wanted to inspect the old model. While the first model, the transfer learning from DeepForest is done, we are still working on training the best version of the UNet that we can train, and we will give it to you with your report in the next 2 weeks. And for what regards to inspecting the old model, we have started, but it's not over, and more could be done. But I don't think it's a priority anymore for us now. So let's start with the first model. The first approach is based on transfer learning, which is the practice to take a model that works well on a certain task, which is similar to the task that we want to solve, take that model and apply it to our task, and maybe change a little bit the model, fine tune it so that it can optimally solve our task. This is great because it sort of transfer knowledge that the model has acquired on one task and it transfer it to a new one. And in a way, it's sustainable because you don't have to spend as much time to train the model as it has already trained it on a similar task. And and we don't have to do all the process again. So this is something that I learned here at Front Punch. The model that we use as a basis, as a starting point for transfer learning, is DeepForest. DeepForest is a tree detection model that was created by the researchers at the University of Florida. And it's also shared in an amazing way with a very good Python package that is super nice to use. Not like it's also very easy. Of course, you have to spend a lot of time on it, but it's easy. The model is based on a RetinaNet architecture, which was also, I think, the architecture used by the previous model from Just Dig It. So there is a similarity, but maybe a difference is that it was trained on the Dion dataset, which is a very huge dataset with a lot of annotated trees. And you can see on the right what is the output of this model. This is an object detection model, so it gives you boxes with the trees in the middle. So how did it go with the transfer learning? Well, we started with the out-of-the-box model, and its performances were not so great, with only an F1 score of 6.8%, which is a score of how well the model does. Then we fine-tuned some hyperparameters, and already the F1 score started to grow. Finally, we did some training on the new data provided by the data team, and the F1 score grew a lot, like it more than doubled. It arrived to 54%. How do we compute the F1 score? We use IOU, so intersection over union method, and if we take two boxes. I don't know if you're familiar with it, but if two boxes overlap and one is a label and the other one is a prediction, and they overlap by more than 40% of their total area, when summed together, then we say that the prediction was correct. And so in this way, we are able to compute some metrics to show you how well the model does. On the right, we can also see like some graph from weight and biases, which is a tool that we use to try different hyperparameters and find the best model through different runs of training. So every line is a model that we try to create. How does this model work on the test set? Well, it has got a precision of 54%, which means that when it predicts a tree, in 54% of the cases, it is a tree. It has a recall of 63%, so it manages to correctly predict 63% of the overall labels of the tree, and the F1 score is 58%. These are numbers, but it's also nice to look at pictures. These are some of the best pictures, like some of the good pictures. Most of the predictions are pretty good, and these pictures look really good. So we see every blue box is a predicted tree, and then we can zoom in one picture to see how in orange we can see the labels, and we can see how the blue boxes are almost always together with the orange boxes. So it's actually quite a good model. It has got some bad sometimes it misses, like there are some mistakes. For example, on the image to the left, we see that the model struggles for this image to predict the biggest tree. For example, here where I'm pointing at, one tree has got two bounding boxes over it, or this tree is completely not predicted. And I think this can be improved by resizing the image. So when we have a drone that is closer to the ground, we could use a bigger, we could resize the image to look a bit smaller so that these trees might be easier to predict. But I haven't researched yet into it. And on the right, we see that the model, first of all, predicts a quad or a truck as a tree, which is not nice. And the second problem that we have is that there are some burn tree in this picture that you cannot really see with the naked eye. But now I will zoom in and you will see. These are all like small burned to the ground or dry trees, and the model is having an hard time distinguishing those trees. So sometimes it doesn't work that amazingly, but overall, I'm quite satisfied with how it works. And then we have a UNet approach, which is like the second approach. UNets are a type of architecture, neural network architecture, that can be used to object segmentation. And it was invented by an Austrian university. And I don't know how acquainted you are with data science, but they sort of are based on the concept of dimensionality reduction. So they base themselves on that concept. They reduce the dimensionality of an image, and then they re-increase it and create mask. I don't know if that has helped you. It has helped me, but also if you have more questions, you can ask them to Sai, who is one of the teammates in the call, because he's smarter than me for what regards this. And yeah, we have created 3 different models, RGB, an RGB model only, which used it as a backend RESTnet, so a pre-trained RESTnet. Then we created a model only with digital surface data. And then we created a model that combines with 2 of them. And we don't have yet official results for the model as they are being trained, but we have some preliminary results and pictures that are cool to show to you. So we basically start with an image, and we split it into different into smaller tiles. Also, what you have to remember with the UNet is that while DeepForest was already a package in Python and had all this function all together, for UNet you had to create every function that you needed. So preprocessing was a big task, while for DeepForest preprocessing wasn't a task at all because you already have the function already pre-made for you. So here instead, every little thing was a lot of work for Sai and Natalia. Anyway, we started like this, and then we identified the trees, and we split also the labels into smaller tiles. And then we use the RGB data and the ground truth map to train a model, and we obtained a prediction that would look like this or like this. We have the tree, ground truth map, and then a prediction again. And this is another example. And eventually we would have a bigger map made like this. And from this map, you are able to count the different trees. And also, this is another function on which hours of work were spent. So everything costs a lot of work in this case. What did we struggle with? As you can see, well, we did our best, but not everything is finished, and not everything, like, it looks great, but maybe not everything is great right now. Well, first of all, we started with like the data team did an excellent job at improving the data and providing us with the data, but they arrived a bit late, so we wish we had the data from the beginning. Some of the team member left at inconvenient timing, so our team is reduced to 4 right now, which is not nice. And also it influences how many tasks you can do and how many ideas you can try out. It's more philosophical, more like theoretically speaking, and data science matter, more technical one, is that it's hard to compare different models, like segmentation model and the detection model. They have different outputs. In one case, we have seen some sort of circles, and in the other case, we have boxes. So how do you compare them? That's quite a hard question. And also, we had the Just Dig It model from the start, but that model does output bounding boxes, but it uses different evaluation metric, and it was a very hard task to have the same metric computed for the different models. So even when they both output the bounding boxes. Finally, yeah, in general, there was a bit of lack of documentation and communication on the previous work on the subject. So there were data that were not able to find straight away, and they weren't documented. And also, there was already a model, but we obtained it really late. So we could have learned from the previous model, right? But we didn't. And also, we couldn't provide it as a baseline to how well our model is doing now. So those are all struggles that we encountered. But we also learned something. Well, first of all, we learned that documentation and communication can go to a long way. We also, each one of us has learned new skills, so that's quite like a platitude. But personally, for example, I learned how to use weight and biases, and I learned a lot about some computer vision notion related to object detection. We understood that getting the right data is almost it's harder than modeling in this case. And we also we are really grateful that we could spend $10 on Google Colab Pro, because it really gave us a lot of additional GPU to work together on the task, which was really good. What can be done next? So we will do our best to transfer what we have done, the codes, the knowledge that we have accumulated about the data, and to document it all properly. And hopefully this will be used by a next wave of researcher. And we also would like to maybe give some ideas, like next wave could use a neon dataset to enrich the present data. They could use a normalized difference vegetation index, a very complicated name to some sort of infrared data that could be added to as an input to our models. And then we could use model assembling. I think the DeepForest model is very good at predicting RGB data, but then of course it doesn't use the height model. But then how do you assemble it? You could use different models and create some rules that get predictions from multiple models and combine them. And there are papers that show that this can work in tree detection challenges. And then, of course, as someone from Republic was mentioning, we could create a model to predict only small trees versus one to predict only big trees, and then just combine them, sort of. So these are all the ideas, but it's your turn now. We have done what we could, I think.
Awesome. Thanks, Michele, for the presentation. I see there immediately is a hand raised by Sander.
Yeah, thanks again, team. Again, great to see the work, and nice also to hear the journey that you went through while achieving this. So a cool presentation. Really like it. I like the fact also that transferring those existing DeepForest model to this new model, well, it took some steps, but it proved pretty successful. And the errors that you showed seemed like they could quite easily be solved by some additional training data on specifically those larger trees, or specifically on those trees without leaves. So that looks very promising. And also the results of the UNEP model that you showed. To be honest, I still don't understand what the model does with the reducing dimensions, but I'll Google that later on. But no, from what I've seen, results seem promising. So I'm very curious to see the final results coming out of that model, and definitely something that will take up for any follow work, either by us, maybe another challenge, or with students working on that. So thanks a lot.
You're welcome.
Any other questions? All right. If you come up with any questions, put them in the chat, and we can do them at the end of the presentations. And then we can head on to the last team, the team that has focused on satellite data. And we have Luis here today to present for us.
Yeah. Hello everyone. So I'll just share this. All right. So for our satellite team, our goal was quite different. We had a team that in the end was about 4 persons. 3 was working on AI engineering mostly. John helped us a lot with the geospatial stuff and was taking the role of Scrum Master. I was doing some engineering, and some was taking the role of product owner, and we have Wei that is going to help us with the storytelling and the report. So that's the team. And our goal is to take our ideas to take the drone imagery work and try to see how we could transfer it and scale it to satellite imagery. And why is that? It's because while the drone imagery is very interesting because it has good precision, plus we have the data elevation model, it's kind of slow and expensive. It's difficult to update. So if you want to have new images, you have to set up a mission again, and it covers small areas. So it's not easy to scale this to very large areas. Whereas when you go to satellite imagery, you have the whole planet covered, and you can get regular updates. It's becoming less and less expensive, and there's a lot of different solutions. However, the precision is much lower. It's like 10 times lower. So it can become more difficult to detect objects on such images. But we do have a fourth band that is the near infrared that I think you didn't have in the drone imagery, and we can see on this image here that the trees pop up quite well on this kind of image. So yeah, so our task was to try and see what we could do with some satellite imagery that we had at our disposal, and this is what we could find as solutions. The first was just to do the same work as the RGB and the data annotation team would do, and just label and train from scratch on images. The problem being that this would not benefit at all from all the work that the previous teams did. So that was not that's not what we wanted to do. But we still had a look at it using some labels that we already had. And the second part was second idea we had is to use the drone models predictions and use them as training label directly on satellite images. And for this part, the big problems was how to align the drone label, the drone data, and the satellite data. So we'll see later how it got difficult. And the third idea was from a paper we found early on, was to just take the drone images and degrade them to make them look like satellite data. And then we could directly use the drone labels to train, and then apply the predictions directly on the satellite data, which is very beneficial because we could directly use all the work from the previous teams. The problems there was to find the proper transformations to make sure that our data set for the training and for the prediction would kind of look the same. So for the first part, training models kind of from scratch, there was some work done with unsupervised classification and trying to reproduce a UNet repo that we found on GitHub, and I think John could say a few words about this. I don't know if John is here.
Yes, I'm here. Thanks,
Yeah.
Lewis. Yeah, so the initial exploration, because Lewis made a good point where we didn't want to go so far down, build our own models when the goal was to translate the drone image models into satellite, but we wanted to just explore our data a bit. So one of the with satellite data covering such a large area, we wanted to see, maybe can we get some benefits from using unsupervised classification to generate class data for, see how well it can detect the trees and vegetation using combinations of bands like the NIR and some of the RGB, as well as, how well can we classify stuff that is not the trees, so that we can use in conjunction with the models to better segment the data. Shri found a nice example using very, very similar satellite imagery resolution on GitHub, and it uses the UNet to count trees. We had good success replicating using their data, but in the timeline we couldn't quite get it to work for us. We do explain it a bit later in some of the slides, but there is some potential there, but we didn't want to run away with that while the other groups were working.
Yeah, so do you want me to switch the slides?
Yeah, sorry. Yeah, sorry, I should have directed it. Yeah, so when we did the K-means class of the unsupervised stuff, we just used combinations of like the red, green, and near-infrared band. It made the vegetation sort of visually pop, and with some evaluation with the unsupervised methods, it seemed to distinguish the tree canopy very well from other classes. 8 clusters seemed to work extremely well. Once we got above 10, things started to get quite confusing and the classes started to blur. we sort of saw that the vegetation was falling in these the classes produced by the k-means, which was just in this instance the 3rd and the 5th and the 7th class. And in the images below, you can kind of see the combination of RG, the red, green, and near infrared bands on the left. You can see the vegetation really stands out as a blue color. You can see our k-means results with the little bit of color vomit in the middle, but it distinguishes stuff quite well. And then taking the different classes, we reclassify them, and so we say, okay, so this is trees, this is not, and then we can also apply that, and so we say, okay, this is crops, this is buildings, this is barren land, and so you have these different classes. Can you go to the next one, Luis?
Yep.
One thing that Luis spoke about was we could take the labeling from the drone work. The particular label shapefile that we had access to for the Bamila site, when we were doing combining the data together, we saw there was a bit of offset because there was a spatial reference discrepancy between the two data sets. The satellite data was for a very localized spatial reference for the Bamila site, whereas the drone labels were in the generic WGS84. When transforming them, we couldn't quite get, there was a little bit of offset, but it was enough to just introduce some errors. So the annotations, even when converting them to like a GeoTIFF, they were still offset a bit, so we're getting a bit more noise than we wanted to. I only explored a few transformations between these coordinate systems, but it didn't look like we could get it to line up quite well. And also with some of the extremely small trees and bushes, it just was not distinguishable even with the near infrared in the satellite data. Can you go to the next one? So just taking the shapefile, we've just made a quick method that converts the shapefile to a GeoTIFF to match the satellite data and drone image data file types. Did spatial reference checks just to compare the spatial references of the satellite and the drone, the annotation shapefile data, and just check, do they match, or what potential margin of error is there, and then using GDAL to create to convert the shapefile to the annotation data set. Can we go to the next one? And then we took that research and took sort of unsupervised classes for the, we were just basically guessed and said, this is crops, this is buildings, this is barren, and then used the annotated, the label shapefile that we converted to GeoTIFF as our trees, sliced the large data set into tiles, and then in the particular example, they said because our annotations were on the extent of the sample that we took from Bamila, we just needed to take 20% of the annotation tile and use that. Didn't get it to work very well, so hopefully in the next couple of weeks we could see, but it's not too important if the other groups had success. I'm good on that. And then just some of the issues were just spatial referencing issues. The particular research used 8-band satellite data, which is very in-depth, and we just had the 4, and then maybe just spending a bit more time with the unsupervised classes to just to play around a bit more to just make sure it's distinguished from the vegetation a bit more.
All right.
And that was our exploration.
Thank you, John. So for my part, I was working on this transforming drone images into satellite images, and it was really just following a paper, 2 papers actually from the same team. That is exactly about this, but the goal is different, and they use it for counting cattle, sheep, I think in New Zealand or something like this, and they have kind of exactly the same problems, which is that they have some drone images and for which it's easier to get labels for the cattle, and then they want to scale it to satellite images, and from this article it goes like from this hypothesis that a satellite image is just kind of a degraded version of a drone image. And according to this research article, mostly you can there's a lot of things that are done to the satellite images these days, especially the satellite that we have has a lot of post treatment on the image. It's pan sharpened. There's some geometric corrections, so there's a lot of things that happen between the image and how we get it. But the idea is just that it's just a blurry version of the drone image with pixels that are bigger. So you can just use two steps to go from the satellite image to a drone image, and the first one is just downsampling it. So they mention using bicubic downsampling. So you get to the good sample distance. So here we want to go from 5 centimeters to 50 centimeters, and this is just done by downsampling the image. And then the more complicated part is blurring using a point spread function kernel, which is calculated to match the simulated satellite aperture. And that's where it gets really complicated, because we get into optics. So the satellite image we had at our disposal are from SkySat Planet, and it's sadly, or I mean, maybe because it's better, but it's of type Cassegrain. And you see on the right side on the image that the aperture function for the Cassegrain type telescope is kind of complicated one compared to the circular one. The circular one, you can have easily find an equation for this, and then you can get the idea is to get the Fourier transform of this. But for the Cassegrain type, they don't explain well on the article how they obtain it, but you were supposed to get this image on the down right of the screen, and then you convolve it with the image to have the deformation of the telescope. So that's where I've looked into it for a while and tried to find how to get this kind of Fourier transform, but it got really complicated, and I think I would need like some kind of optics specialist to help me with this. But so anyway, I took the idea and I went ahead and said, okay, let's just try something simple. And you can use just some kind of Gaussian blurring, which is a way to approach actually the PSF of a circular telescope. So if you look at this, it actually kind of looks like a 2D Gaussian that you can then convolve with your image to blur it, which is a typical augmentation method you could use in image classification or anything. You can add some blurring, and sometimes you can have augmentations like this. And so here, what it looks like on a sample drone image. So the first image here is the drone image. Then you apply blurring to it, and then it's the same image, but you still have like 1,000 pixels. And then you use the downsampling, and you end up with a 300 pixel image. So it's just. I don't know if it's you can see well how it degrades the image, but the idea is that here it's a little bit more blurry, and it looks more like a satellite image than a drone image then. And if you compare the same sites from the degraded drone to the satellite, then you can see that there's still a lot of work to do, and mainly I guess on the colors as well. And I guess because it's also because of the fact that this image is pan sharpened. So pan sharpening, you may look into it afterwards, but it's using different precision images to just apply the color to have the good contours of the different objects. But yeah, so this is where I ended up at, and so. And the idea is, if you train on a model on the left image and try to predict on the right one, I guess my guess is that they're not close enough, so the model would work. So there's a lot of lot more work and lot more fitting of the different transformation that we would need to do for this to work. And so that's where I ended up. So my conclusions about this whole project is that I guess the best option if we wanted to do this task is just to make sure during the data collection strategy to use the same projection for the drone and the satellite, and that would greatly simplify what we wanted to do. And then yeah, I've said that more work would be needed on the image degradation. Starting from scratch on the satellite data could be a viable option as well, because I think that what John showed, like it's easy to get not easy, but we can get some decent results. So with some unsupervised methods. So, but we could also, with a substantial labeling effort, have a good supervised result. Yeah, and yeah. So one last point, I think it's kind of the same that Michele mentioned. It was very difficult for us to organize volunteering work on top of our jobs, all of us being from 3 different time zones. So it was a big challenge, and we literally had a lot of difficulties meeting each other. So yeah, so we still had some good sessions from time to time, and I think more than results, we have some things to explore, some new things to explore, and some advice on how to go with it. So yeah.
All right. Thanks, Luis and John, for the presentation. It's very nice. Sander has his hand already raised again, so go ahead.
Thanks. Yeah, thanks again, team. Yeah, again, good work. And I know this was challenging. Since originally we did not even plan to add the satellite data questions to this challenge, we thought, well, let's focus on the drones. And then during the kickoff presentation, there were so many questions on the satellite data and so many enthusiastic responses in the Slack as well. So, well, let's give it a try. And indeed, it's challenging. And it sounds so easy. You have 2 different data sets of the same village. So how hard can it be to overlap them? I've been playing around with that myself also a lot. I think it's not just in the projection that we chosen for the drone or that the drone is giving to us. I think it's also in the inaccuracy of the drone results and the satellite data results. Since I've been trying to manually overlap several drone and satellite images for different villages, also using different projections and transformations, it didn't line up. There was always a couple of meters offset, and even if you correct it in one place, then it's off on another place. I did get it okay-ish in some of the sites, but there does not seem to be a fixed rule. And we even tried tweaking with the projection settings on the drone and things. I think it's just the inaccuracy and the difference in the way that the data is captured by the drone and by the satellite, that there is a difference. I think there are ways to improve it, so I'd love to chat a bit further with you, and maybe we'll do that over Slack to see. I know for a couple of sites, I managed to get it quite okay. So would love to hear from you if that would be useful, if I share the transformed images that overlap reasonably well, see if those are of help to you. And then on the last images that you showed, while you were transforming the drone image into some sort of satellite image, yes, they look pretty different. On the other hand, the trees, they stood out quite clearly, and this seems fairly similar in both images. So I'm very curious what would happen if you would run the model with the labels of the satellite data, and how good or bad the outcomes would be.
Yeah, so that's what I would want to try for the rest, but sadly we are kind of missing workforce here, so it's only me that's left, because both John and Ray had some job change that they need to have a lot of time, and I thank John again, because he did give us some time again. Well, he's just starting a new job, but yeah, I mean, that's definitely what we would want to try. But I guess my point is that if you can see with your own eyes that the images are so different, it's probably not going to work so well.
All right. Yeah. See, yeah, still be very curious to see if we can pull it up. But otherwise, let's be in touch, and maybe you can prepare it in such a way that we can find someone else to run it.
Yeah.
Thanks anyhow. It's I think some excellent recommendations also for us that we can use in bringing this to a next level in any future work. So well done.
Okay.
All right. Okay, so that brings us to the end of the presentation. So if there are any questions left, make sure to voice them now, put them in the chat. I see Andrea has a question.
Yeah. Hey, do you hear me?
Yes.
Yeah. Hey, I am just wondering, which images did you use for the last procedure?
Sorry, I didn't hear you well. Sorry.
Yeah. Sorry. I am wondering which image did you use for the last for your analysis?
It was from Bamela. So I used the QGIS to overlap a satellite image and a drone image, and then I took a little square just to try on it.
Yeah, but I am wondering from which satellite did
Oh,
you get the image?
it's SkySat Planet.
Okay, so it was a SkySat.
SkySat, yeah.
Okay, thank you.
All right. Any questions left? Otherwise, Louis, you can.
I do have a question to the team and everyone present. So I'm very curious to hear the biggest things that you've learned or experienced during this this exercise and the past 10 weeks or so that you've been working on this. Maybe if someone can respond, a few of you very curious for us to learn.
Yeah, I'm curious to hear that as well. Louis, you can stop sharing. Then,
yeah.
Great.
I guess one thing that I really enjoyed learning was everybody's looking at all the different groups and, working with folks in my group was the methodology that people approached the data with, because I wasn't too familiar with artificial intelligence and ML, and just looking at how everybody approached it gave me a lot more insight into the way to start the pre-processing, how to set that up. So it was interesting. Also, never really worked with Google Colab, so it was very good utilizing that. Probably utilize it a lot more.
All right. Yes, John. You're a GIS expert, right?
I'd like to think I am, but I'm wrong sometimes.
Yeah. Nice.
Thanks, Cool. I can fully imagine that, seeing the presentations today, so many different angles of approaching, trying to find a solution, and many of them quite successful on their own.
Exactly. Yeah, I'm myself very impressed as well. So as briefly mentioned before we started, the team still have 2 weeks to finish up the reports and run some final models if they want to. In 2 weeks, we will deliver all the code and the models, plus all the reports to just dig it. But we will also open source all our results. So the data set, we will have a short conversation about that, Sander, later on how we're going to do that. But eventually, we will open source those as well. But if there are no more questions left, then yes, Sander, do you want to do some closing words?
Yeah, thanks. Although I must apologize, I sound like I have a sore throat, which indeed is the case. I've been ill the past few days, so I hope I'm still audible. But it's been great to be working with you and to see these results now from the different groups. And exactly as John was saying, this is something that we have been working on as Just Dig It, also together with Tom and some other partners for a long time already. So then you've been trying to scout for solutions and approaches, and kind of coming up with what we call in Dutch a tunnel vision of one approach that will hopefully lead to a solution. But now seeing all the different groups presenting all those different approaches, which all make so much sense, it's really helped us. And it's not just the results that are being presented here, which in themselves are very useful to us, and something definitely we can take up for future work to refine them and use them in our day-to-day operations. But also the approaches towards that. So what are the useful ones? What are things that have potential but need further tweaking? So those are definitely going to help us as Just Dig It to improve what we are doing. And so we're very thankful that you've all been engaged in this. And actually, as Just Dig It, we are a relatively small organization with huge ambitions. So we have a team of about 40. We are growing rapidly, but still 40 people trying to regreen the whole of Africa. That's not much. So we really rely on our partners, and those are our partners on the ground that do the hard work in digging these half-moon water buns, pruning those trees, trying to educate and convince farmers to participate. But it's also partners like you that help us to improve our workflow, improve our efficiency, improve our learning of where we are doing well, where should we improve our efforts. So, big thumbs up to all of you in the work that you did. That's really helping us to achieve more impact, learn where we should put more emphasis on, but also to tell that story to the world. That's the other part that we as Just Dig It are doing. We are doing the regreening on the ground, but also the storytelling around it. And those things that you have been working on, they help us to make it more tangible. Since, yes, we do communicate on our website that we brought back 10 million trees. Still, it's such a large number, it's hard to make that tangible for many people. But we've already seen by showing photos on the ground that can help. But I think bridging that step to drone and satellite data makes it so much more alive. And I'd love to have that combination of the data that we get from our trainers, the people on the ground, having the photos as proof from the field, but then to back it up with more scientific data to show the scale using the drones and the satellite data. And that's what we need this for. So yeah, a big thumbs up to all of you. Great work. I'm really looking forward to the final model runs and the presentations in the coming few weeks. Thanks already so much, everyone, and been a pleasure to work with you.